Hey, welcome back. In the first video in this series, we defined and described multivariable functions and saw some examples of how to evaluate them and some examples of how to create them. Now inside this video, we're going to talk about how to take their derivatives. For a function of two variables, and we'll talk about three variables as well, but starting with two. For a function of two variables, we'll find that there's two ways to take the derivative, two ways to take the first derivative. We could either take the derivative with respect to x, or we can take the derivative with respect to y. The derivative with respect to x is defined as the limit as h approaches 0 of the difference quotient, where the difference is being applied to the x variable only. So we have f of x plus h, comma y, minus f of x, comma y, all divided by h, being our difference quotient. So we're only changing the x-coordinate by a small amount and seeing how sensitive is the output of the function to that small change in the x value. For the y derivative, the only change is we're looking at, instead of x plus h, y plus h. So how sensitive is the output of the function to a small variation in the y-coordinate, leaving the x-coordinate the same. One of the curious, semi-weird things about derivatives of multivariable functions is that they, first of all, have a different name. Instead of calling it the derivative, we call it the partial derivative. And the second curious thing is that instead of using the d for the derivative, we use a curly d for the derivative. I'm going to pronounce it di, so dif by dx instead of df by dx. D means difference. Curly d, di, means partial difference. One consequence of moving to two or more variables and functions is we can no longer use prime to denote a derivative because the prime is ambiguous. The prime does not tell us if we're taking the derivative with respect to an x variable or with respect to a y variable. So it's got to go. Can't use it. I'm actually not going to do this example in video format the hard way. I invite you to do it on your own. Try it on your own. You're not tested on it. It's good for your soul to do at least one partial derivative independently of any shortcuts. And at the end, if we're taking the derivative with respect to x, make sure that you get the following. That f sub x, which I forgot to mention in the previous slide, f sub x and dif by dx are both acceptable notations for the partial derivative of a function with respect to x. So that's a subscript x. So anyways, at the end, this dif by dx, or alternatively f sub x, what you'll get is 6x plus 5. After going through that long process. And you may be able to look up at that and convince yourself why that's going to happen using the definition of the derivative that was on the previous slide. That any y term is going to stay exactly the way it is, like there's no y plus h for the x derivative. All the x terms are going to get the x plus h thing being added on, and it's going to look just like the definition of the derivative for a single variable function with this y stuff tacked on and then subtracted when we do the minus f of xy part. The interesting thing is what happens when you have a component of a multivariable function that has the x and the y parts multiplied together. Then you get interesting things happening, and we'll see some examples. The way that we're going to take partial derivatives in this course is we're going to use shortcuts. So the shortcut that we'll use to take the derivative of a function like this one, 7x squared plus 3xy plus 4y squared, is we're going to use the power rule, and we're going to use another rule. So we're going to use d by dx of x to the power of n is n times x to the power of n minus 1, and we're going to use one of the underappreciated rules in calculus for derivatives. The derivative of a constant times a function. Derivative of c times f of x, which is c times the derivative of f of x. The rule that allows us to factor a constant out front. Now, constants, we will see, don't requirements to be a constant are kind of fluid. It's enough to be a constant with respect to one variable in order to factor it out of a derivative of that variable. So I'll show you what I mean inside this example. We're going to take the x derivative of this expression. So f sub x is the x derivative of each of those pieces. So die by die x. I know my dies look a little bit like 2's, maybe a little bit too much like 2's, and it's just hard to draw a curly D. I'm sure you'll find the same when you're making your notes. So die by die x of 7x squared plus, now we're going to take the x derivative of the next piece, die by die x of 3xy, plus die by die x of 4y squared. I guess we're also using the derivative rule that the derivative of f plus g is the derivative of f plus the derivative of g. So we're distributing the operation separately to each piece that's separated by a plus sign or a minus sign. Okay, now what we're going to do next is we're going to use the constant factoring rule, the second rule that's written off to the right hand side. We don't usually write this, but I'm going to do it. I'm going to take the 7 and put it out front. It's 7 times die by die x of x squared. The next thing, 3 is a constant, but for the purposes of the x derivative, y is also a constant because y is an independent variable. Y is not dependent on x. This is not implicit differentiation. So when I take the 3 out, I'm also going to take the y out with it. So die by die x of x plus, and for the next one, there's nothing left. When I take constants out, I'm going to take the 4y squared out. I'll have the x derivative, die by die x, of just 1. So y is a constant when we're taking the x derivative. Now we'll take the derivative of each of those pieces using the power rule. We'll have 7 multiplied by 2x plus 3y multiplied by 1 plus 4y squared multiplied by 0. And then simplify. 14x plus 3y. And a good question to ask. Put your hand up, ask, do I have to show all those steps? No. Once you get the hang of this, once you get good at this, you just go directly to the last line in one step. But until you get good at this, until you're able to mentally block y from being treated like a function, I highly recommend writing out these steps and these types of rules. Eventually it'll be second nature, but it's usually not at the start. So just to highlight that a very important step where we acknowledge that when we take the partial derivative with respect to x, any other variable is considered a constant. If you look at that bottom calculation, the partial derivative with respect to x of x to the power 4 times y to the power 7, we treat y as a constant, so the constant term, the y to the power 7, can go in front, and then that's multiplied by the derivative of x to the power 4, 4x to the power 3. So I'll just break down the answer here. We'll get y to the 7 times 4x to the power 3. And then, as is traditional, constants go in front, and then x values go afterwards, and then y values go after x values. Now if there are z values, they'd go after that. For the y derivative, it's just switched. Whenever we take the y derivative of a multivariable function, we treat x as if it's a constant. And then we do to y whatever we would do to x. This is not implicit differentiation. This is not the chain rule. This is just changing the letter that we're working with. So going back to that same function, we'll take the y derivative of it now. F sub y is the acceptable notation for die f by die y, f sub y. We'll have the y derivative of each of those three pieces, die by die y of 7x squared, plus die by die y of 3xy, plus di by dy of 4y squared. And now we'll use that rule where we factor constants out front, but the y part is not a constant anymore. Now the x part is a constant. Its constantness is related to what type of derivative we're taking. So it's context dependent. For the purposes of this calculation, x is a constant. For the purposes of this previous calculation, y was a constant. So it depends on what we're doing. Where the derivative means to vary one of the variables by a certain amount. The x derivative means to change the x variable by a little amount, but not the y variable. The y derivative means change the y variable a little amount, but don't change the x value. That means since we're not changing x, x can be treated as a constant. Anyway, let's keep going with this. I'm going to take the constant stuff out, the 7x squared. And we have the y derivative di by dy of 1, what's left over, plus I'm going to take the 3x out this time. Now we have the y derivative of y, to the power of 1. And then I can take the 4 out, but the y squared has to stay, because y is the variable now, not the constant. And now let's take the derivative of all these pieces. We have 7x squared times 0, since 1 is a constant, plus 3x times 1. The derivative of y with respect to y is just 1. And then the derivative of y squared with respect to y is just 2y. So 4 times 2y. It's not 2y prime, not 2y times y prime, rather, because we're not taking the derivative of y with respect to x, where y is a function of x. We're taking the derivative of y squared with respect to y. Very, very different. Okay, so we'll get 0 plus 3x plus 8y. So 3x plus 8y. All right, a little more complicated. Now we have a mixture of x's and y's. It can't be disentangled, and we want the y derivative of it. So I've got some good news. The good news is that all of our old rules, the product rule and the quotient rule, for example, hey, they follow us. They don't disappear, but we have to use them with a little bit more care. That's all. So f sub y, this is a top function over bottom function, so we'll need a quotient rule. This is going to be the bottom function times the derivative of the top, but not just any derivative. Since we're taking the y derivative, it's not going to be t prime, it's going to be t sub y minus the top function times b sub y divided by the bottom all squared. So that's the quotient rule for a y derivative. The quotient rule for an x derivative would just have t sub x's instead of sub y's, or b and t sub x's instead of sub y's. Okay, off to the side, I'm going to do these calculations for t and b derivatives. T is x minus y. T sub y is going to be the y derivative of each of those pieces, di by dy of x minus di by dy of y. So we'll have 0 minus 1, just negative 1. And our bottom function is x plus y. So b sub y is going to be the y derivative of x plus the y derivative of y. The y derivative of x is 0. The y derivative of y is 1. So we get positive 1. And we'll plug those into our formula. So the bottom function, which is x plus y, times t sub y, so times negative 1, minus the bottom function, minus the top function, x minus y, times b sub y, which is positive 1, all divided by the bottom squared, x plus y, all squared. Now that itself might be a good answer. I mean, just you may want sometimes to leave it like that. But once in a while it pays to simplify. So simplifying, multiply the negative 1 through the first bracket, negative x minus y, multiply the negative through the next bracket, negative x minus minus, so plus y all over x plus y all squared, and then collect like terms. Negative x, another negative x, then negative 2x, negative y plus y cancels. And this is our answer. I'll call that option. I'll call alternative. Simplified. All right, here's another one. We want to take the derivative of this function with respect to y and then evaluate it at 2, 4. So this is a two-step process. Part 1 is to find df by dy, and part 2 is to evaluate it at 2, 4. Okay, so here we go. F sub y is dy by dy of e to the xy. That's going to be, we're taking the y derivative of e to the power of w. So our derivative is going to be e to the w, not multiplied by w prime, multiplied by w sub y. I'll write that down. Instead of e to the w times w prime. It's e to the w multiplied by w sub y. Okay, so e to the w, e to the xy, multiplied by the x derivative, or the y derivative of xy. So I'll put that off to the side. W is equal to x times y. W sub y is the y derivative, dy by dy of x times y. We can take the x out front, since for the y derivative, for the purposes of that, x can be treated as a constant. We're not varying it. So we have x multiplied by 1, which is just x. And that will go in that box, and that'll be our answer. If this was an implicit differentiation question, if we were asked for f prime of x, where y is also a function of x, we would have a very different answer. We would have the derivative of x times y using the product rule. We would have xy prime plus y. But we don't have that. It's very important to not confuse multivariable functions with implicitly defined functions. And for implicitly defined functions, y is a function of x. For multivariable functions, you pick anything you want for x, you pick anything you want for y. Their values are not mutually tied together. Okay, we have 3 variables. What changes? For the 3-variable derivative, or 3-variable functions, nothing. We have x derivatives defined the same way. When we take the x derivative, we treat 2 variables as constants now. Anything that is y or z, for the second and third variables, we'll treat those as constants. For the y derivative, now we treat x and z as constants. And now the new one, the z derivative, we will treat x and y as constants. The key to doing these correctly is to use that derivative law consciously. That the derivative of a constant times a function is a constant times the derivative of the function. And at least at the beginning, to write out those steps. Don't skip them. Don't think it's beneath you to write out steps. Whatever someone thinks about silliness, about showing work and showing steps, do I have to do this? Should I do that? The answer, I guess the best way to think about this is, does it help you get it right? If so, it isn't silly, and it will help you get it right, to think, especially at the start, to think about that step consciously and to write it out. So let's look at a concrete example. I want to find the 3 different first derivatives, fx, fy, and xz, for this function. So I'm going to split the screen into 3. Hope that's enough space. So we'll start with f sub x. So we'll take the x derivative of the first term, y times a lot of x, plus the x derivative of the second term, di by dx of z e to the y. And consciously think about that rule. For the first part, y is a constant, so I'm going to take it out front. Y times the x derivative of ln of x. For the second part, z is a constant and y is a constant. If y is a constant, then so is e to the y. I can take that whole block of stuff and put it out front. Z e to the y times the derivative with respect to x of 1. Underneath I'll say we treat y and z as constants for f sub x. Well, that's for, let's say, during f sub x, while we're taking the x derivative. When we're done taking the x derivative, hey, they're back as non-constants. So again, this is contextual. It depends on what we're doing. We're treating them as a constant right now, temporarily, for the purposes, only for the purposes of this calculation. But when we're done the calculation, they're back to being variables. And I should write this. If y is a constant, so is e to the y. E squared is a constant. E to the 7 is a constant. It's 2.71828 to the power of 7. So just some weird decimal number. All right, let's complete the derivative. We'll have y multiplied by the derivative of ln of x with respect to x. Derivative of ln of x is 1 over x. Plus z e to the y times 0. Derivative of 1 is 0. So we just have y over x as our answer. Okay, next one. Now we want the y derivative of what's there. So f sub y is the y derivative di by dy of y times ln of x plus di by dy of z e to the y. Now we consciously think about what we treat as constants. Treat x and z as constants. And if x is a constant, ln of x is also a constant. Like ln of 3 is a constant. It's some decimal number. Okay, so ln of x can come out front, and we have the y derivative of y. Z is a constant, it can come out front, and we have the y derivative of e to the y. And then let's take the derivatives. Derivative of y is 1, so we have ln of x multiplied by 1, plus the derivative of e to the y with respect to y is just e to the y. So we have ln of x plus z e to the power y is our final answer for fy. Now we have the last derivative term. F sub z. So we're going to take the z derivative, di by dz, of the first term, y times ln of x, plus the z derivative of the second term, z e to the power y, and then think about what's a constant and what's not a constant. So now we're going to treat x and y as constants. So the y and the ln of x will come out of the first term, y times ln of x times the z derivative of 1, plus e to the y can come out, times the z derivative of z. So we'll have y times ln of x times 0, plus e to the y times 1. We get 0 plus e to the y, which is just e to the power y. So those are your three first derivatives for this multivariable function. Okay, and then the last one, how do you take the first derivatives of this thing, a product of x squared y to the 4 z to the power of 3? Do you have to use a product rule? So let's carefully write out each of them, and I'll show you that you don't need a product rule. F sub x is the x derivative, die by die x, of x squared y to the 4 z to the 3. We can factor the constants out front. So the y to the 4 is a constant as far as the x derivative is concerned. Z to the 3 is a constant, and we have the x derivative of x squared, which is 2x. I'll make a little note here that we treat y and z as constants for the x derivative, the partial derivative with respect to x. Okay, now I'll do the next one. F sub y, die by die y of the same thing, x squared y to the 4 z to the 3. Now we're treating x and z as constants. So I'm going to pull x squared and z cubed out front. I will have the y derivative of y to the power 4. So I'll have 4x squared y cubed z power 3. I'm writing these final answers in standard form. Constant, like the real constant out front, the 4 or the 2, and then the x thing, and then the y thing, and then the z thing. Again, on the last one, f sub z. Now we have the z derivative, die by die z, of the same expression. Oh, I should write this down, that we're going to treat x and z as constants. Now, for the z derivative, we're going to treat the other two variables as constants. So we're going to factor the x squared out and factor the y to the 4 out, and we have the z derivative of z cubed. So 3x squared y to the 4 z to the 2 will be the answer. And we treated x and y as constants. Right, and we'll continue the next topic, the next video.